Hello. Just checking. Yeah. Hello. 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 I'm just checking for echo right now. Hello. 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 Good evening, everyone. So, this is supposed to be the week 12 class, but as a part of the extra 2 hours that I've chosen to take, this is the week 12.5, you can call it, or rather the extra class. So, ideally, the first agenda here is for us to complete week 12's questions. We have 4 of those. Right? We have 4 of these questions here. I mean, sorry, we have 10 of these questions here. Right? We'll complete these. But before that, I thought I'd take the opportunity to talk about the whole course, right? So I thought I should bring some perspective to what it is that you folks have learned in the past 12 weeks. And and basically give you context in terms of networks and where everything that you've learned fits in, right? And then probably we can move to the questions, or probably I think, yeah, okay, fine. So let's finish off this first, and then let's move to the perspective, right, which will kind of like end the lecture series for this NPTEL season. Okay, so let's look at the questions. So what is the fundamental concept behind named data networking? Right. Okay, just before that, I think wait. Hmm. Okay, good. All right, so we were looking at named data networking, and here, just a moment. The question is, what is the fundamental concept behind named data networking, right? So NDN was something that we elaborately saw in the previous class. So is it IP addressing? Is it host-based addressing? Is it content-based addressing? Or is it MAC addressing, right? So IP addressing is something that all of us should be quite familiar with right now. This is nothing but the current paradigm of using IP addresses like 12.0.2.1, let's say. This is basically the address of a particular host, and we route to this particular host through the internet, correct? So this is the current de facto standard IP addressing. But is this the fundamental concept behind named data networking? No, it's not. B, host-based addressing. So again, IP addressing is also used for host-based addressing. So this is also not the answer. It's content-based addressing, right? So basically, content-based addressing is what NDN does. So it names the it names each of the uh, resources on the internet, and then based on the name, you tend to kind of route to it. Correct. So this is pretty much the fundamental behind it. And then finally, MAC addressing. So MAC addresses are used currently, but they are used in private networks where you have local switches, and these switches, I mean, towards the last mile delivery, when you have to finally send a packet, and that packet goes and sits, the packet goes and has to go to the correct host in the local network. Let's say. Right. So I think some people have joined just now. So just before that, the agenda for today, I would just like to repeat it. So the week 12 questions are about 10 questions are there. We'll complete these 10 questions. And on top of that, I also thought we should put into perspective what it is that you folks have learned all across this NPTEL season. So we'll kind of like briefly go through everything that you've learned for the past 12 weeks, and I'll tell you where they fit in terms of the current networking paradigm and what it is that you have learned. Okay, we'll go week by week, and then probably we'll put it into a picturistic format where you can understand, okay, this is where things fit. Um, right, so that's the idea. So first, let's complete the week 10 questions, and probably I expect to complete this week 10 questions in 1.5 hours. And the last 30 minutes, let's discuss or let's conclude the set of this whole NPTEL course. Let's conclude it, right? Right. So I'll just write down some aspects here. So traditional networking are based on end-to-end communication using host addresses. And an example for host address is IP address. I hope this puts it into perspective. So basically, what this means is data is sent from one specific host to the other. So when data is being sent from one specific host to the other, it is done through IP addressing, so which is the first two options. So what happens in NDN? The communication paradigm. Just a moment. Shifts from addressing hosts to addressing pieces of content by name. So what this implies is that each piece of data is identified by a unique unique name rather than by a location or IP address. So what this method does, so this simplifies data retrieval in networks. So essentially, this is like the biggest, the big nutshell or summary of NDN. Right. Um, so and again, so A and B are wrong, and then D is also wrong. So C is the answer, right? So this is NDN. I think this would serve as a kind of a refresher to what NDN also is, right? Um, so I think some people have joined just now. So just to those folks who have just joined, just letting you know that for 1.5 hours, we'll finish off the 10 questions in detail. And then for the next half hour, we'll put into perspective what was learned in this whole NPTEL course. We'll go through each week and with perspective of what you've learned and what are the future aspects of in that particular week's topics, right? So just mind back. So in NDN, what is the purpose of the interest packet? Correct. So are they asking whether this interest packet is used to acknowledge a receipt or to establish a connection, or is it used to advertise network status, or is it used to request content? So I think the answer is pretty straightforward here. It is to request content, right? So what is the context behind this? I'll just write it down. So NDN operates through a request response model where data is pulled from the network when requested. So an interest packet an interest packet sent by a consumer to request a specific piece of data based on its name. So what happens when an interest is received? So when an interest is received, routers forward it towards a potential source of the requested content. Right, so with this context, I think the answer is to request content, but let's just look at why the other answers are not right. So to acknowledge receipt, so that means that you are acknowledging that you've received something. So this is pretty much not the purpose, right? Acknowledgements, basically they are a mechanism in other protocols. For example, TCP. Right? So this is something that's used in TCP, right? But something that is used in NDN's interest or data exchange. This is wrong. And establishing a connection, right? So NDN is connectionless. So essentially what this means is it does not establish dedicated end-to-end connections like TCP does. Right? So this is also not. And to advertise network status. So basically networks, the way they work is that they tend to share the network status with other nodes or other middle boxes in the network. And network status information is basically conveyed, right? Through a different special packet, let's say. But in this case of NDN, network status information is not conveyed by interest packets. Uh, these interest packets, they only serve as a mechanism to request content. That's pretty much it. Right? So this is also not the answer. So the answer is D. So now, which networking architectures address the limitations of content delivery in current networks by focusing on the content itself? Um, so the question basically what they're asking is there are some internet architectures, right? Some of them are being used, some of them are just research-based are just conceptual ideas which have not been implemented on a large scale. They're asking among these multiple ideas, let's say there is architecture A, B, C, D. So which of these models address the limitations of content delivery? So what is this content delivery? Content delivery is nothing but um, transporting information from one part of the internet to the other. But in a specific term, content is basically like large chunks of data, like movies, right? Videos, etc., etc. Right? So delivering such content specifically becomes a bit of a challenge because let's say a movie, let's say a recent movie, right? Let's say a movie. What name should I take? I don't remember a movie, but let's go with I don't know. Let's say Snow White. Okay, right. So because this movie has to be transported to multiple nodes, it's the same copy that's being sent again and again and again on the internet, right? So isn't this a bit inefficient? So if in the world, in the globe, this movie is here and then you are here, your friend is over here, right? This movie has to be sent to you also, and then this movie has to be sent to the friend also. Right? So if you can take this movie and put it somewhere close by, the distance it travels is very less. So this is where we try to, as human beings, right? We've come up with a particular architecture, and then now we try to find ways to iterate over it and make the and increase efficiency and everything. So these models or these different architectures come in this context, and they're asking which of these address the limitation of content delivery in current networks by focusing on the content itself. Okay, so I'll just give you the context now. Modern communication networks were built for post-based interactions. However, the rise in content distribution demands. Um, I wonder. Okay, I think Vardharaj, your mic is unmuted, so you can mute it if you can. मला कधी कळलं माहितीये काय हे बघून कराले थोडं थोडं केलं ते ना स्वतः ते जे आयडी फोल्डर आहे ना ह्याच्यावरनं समजलं त्यानं माझ्या प्रोजेक्ट रेफरन्सला मागितलेला आयडी फोल्डर फक्त नेक्स्ट यूज होतोय होय आणि त्यानं रिॲक्ट मध्ये टाकला Vardharaj, I think your mic is unmuted. You can mute it, right?
Since there are doubts, the great questions from the that are coming to the rest of the record करायला नाही record नाही आलेलो असतो between चौघ जण त्याच्यामुळे काय होतं तुझ्या दोघं जण होते मी आलो पण
All right. I think I'm forced to mute your mic. I'm sorry. Oh, okay. Right. Content distribution demands, right? Like, so what are these demands? They are video streaming, large scale content distribution, has led to the development of architectures that focus on content rather than endpoints. Right, so in this context, both be content centric and named data network. Both emphasize addressing and retrieving data solely based on its name or content, right? The location of the data is not important. It's not the key factor. Because currently IP address means you have a location of that particular data, right? And that's completely removed. So which is why content-centric networking and named data networking are focusing on the content itself. Right, so what are these peer-to-peer and content delivery networks? Let's take a look. Right? So these P2P networks, right? They distribute content among peers. That is, you can be a peer, I can be a peer. Anybody who is in the internet can be a peer. For example, this is peer one and this is peer two, let's say in this diagram, right? And you can exchange content among yourselves. So these do not inherently shift the network model to content-based addressing. So they focus on decentralized resource sharing rather than fundamentally renaming data for retrieval. So what are CDNs? So basically CDNs enhance the delivery of content by caching it closer to the consumer. But they still rely on traditional IP-based routing mechanisms rather than a content-based approach. Okay. So basically CDNs in the context of this picture, I said that we'll be shifting the main server from here to here. So these are all CDN nodes. So they bring the data closer to the intended recipients, right? So because they're closer, you don't have to traverse all the way. So your network bill comes down, right? So, but both of these they still use our IP networks. They don't use any named data networking concepts, which is why the answer for this is A and C. Right? So in NDN, what component is responsible for maintaining a record of interests forwarded by routers until corresponding data packets arrive? Is it A, the content store? Is it B, the forwarding information base? Or C, the content information table? Or D, the pending interest table? So again, just by looking at this question, if you had seen the videos, you might know that the answer is D, but let's take a look, right? Just I'll be back in 2 minutes. Apologies, sorry for that. So it is called the pending interest table. And what the context behind this pending interest table is this. So NDN routers must keep track of outstanding requests, interests, let's say, so that when the corresponding data arrives, it can be forwarded along all paths. Where the request came from. The PIT, right? The pending interest table. It's a data structure. It's a data structure in Indian routers that records each interest packet. What does it record? It records its content name, and the incoming interfaces. So when the data packet arrives, the PIT is used to forward the data all requesting interfaces. So this is basically what the PIT does, and that's pretty much the answer to this. So the content store, right? So what is this content store used for? This content store is used to cache data packets, right? So this is used to cache data packets, not for tracking pending interests, right? So the forwarding information base, right? What is this used for? So this is used for routing decisions, right? And it is not used uh, for maintaining state about pending requests, right? And C, which is content information table. This is not even a component in the Indian architecture. This is just a placebo that's been kept there to throw you off, right? So the answer is B. So in NDN, how are data packets forwarded towards their destination? So based on what are these data packets reaching the intended recipient? Is the question. So the key aspect to remember here is, unlike traditional IP, which use IP addresses for routing, NDN uses names that represent the content. Right? So now I think it's time to look at the options. Is it A, based on source and destination IP addresses? No, this is IP based routing, right? This is what we do now. This is not the answer. So is it based on interest packets and content names? Yes. Is it based on MAC addresses in the data link layer? So this is link layer addressing and it is not used for routing. This is link layer addressing. And it is not used for routing data packets. At the network level. So this is also wrong. And based on port numbers in the transport layer, I mean, port numbers, I think this is from basic networks. Port numbers are related to transport layer connections, like TCP port, UDP port. And these are not the basis for data retrieval in NDN completely. Like, it is just not at all. So I think you can pretty much easily say that the answer is B. So which of the following statements is or are correct? So how many of these are correct? Correct. So in NDN, content retrieval primarily involves three types of packets: interest, data, and control packets. So we've seen this, and we've also seen this, right? So this is true. Right? NDN can use hierarchical naming convention for routing and caching of its packets. So this is also true. How is this true? When you name a movie, let's say that movie can be named as comedy slash fiction slash movie name. So this is a hierarchical structure that you're creating. And so this is also true. That pretty much is what Indian is all about, right? And C is in Indian, content is secured directly rather than securing the transmission channel. This is also true. So content is directly secured using um, cryptographic mechanisms, which you can basically use to ensure that the content is integral and it's authentic, right? So this is also true. And content in Indian is cached in the downstream direction along the reverse path of the corresponding interest packet. So this is also true, which means I've done a mistake somewhere. Let's figure it out. So this is also true because you have, let's say, multiple nodes. Right, so this is upstream and this is downstream. In a way, that's how it is connected. So this is from your end, and this is to the major internet end, let's say. So this is upstream, and this is downstream. So if you're requesting something, this is cached somewhere downstream, right? This is downstream. So that's what this means, and this is also true. But okay, so this is true. D is true, C is true, B is true. When I think, yeah, right. So this seems to be a problem. This is pretty much why I think we can rule out A as false. Right, correct. So the answer is A. So the point is there is interest packets, there are data packets, there are nothing called control packets in Indian. These are not even there, not in Indian. In case if they give the same statement without control packets, and this is also true, right? So again, see, mistakes can happen like this. So yeah, so the answer is B, C, and D. Right? Okay, this is a big question. Let's break it down. Two consumers, right? C1, C2 express interest in the content XYZ dot MP4. I don't know if nowadays MP4 is used. By sending interest packets to the network. an intermediate router R1 between the content consumer. So these are the content consumers. And this is the content provider. And where is this intermediate router R1? So this R1 is kept over here between the content consumer and provider in the network. It initially receives an interest packet for content xyz.mp4 from consumer C1. So initially, what does it receive? So of course, these are all connected. Okay. So what does it receive? It receives a interest packet. I'm calling it int1, and it's coming from C1. So now they are saying, okay, since the content is unavailable at router R1, correct? So this router is right now, it's pretty fresh, it's new. The network has just booted up. Okay. Since the content is unavailable, right? It's not available right now. It's unavailable at router R1. It adds the incoming interface and interest name to its pending interest table, correct? So what it does, what this router does, there is this pit table, correct? The pit table is over here. So what does it add? Let's say this is interface 1 and this is interface 2. Okay. So the pit table is something like this, and it has the interface. Interface is nothing but port. Okay. The physical port of the router. Interface and the interest name. Right. So what is the first entry here? The first entry here is 1, and then the interest name is int1. I'm just visualizing whatever is being written here. So we are here at the question, right? So interest table. So basically what it is, from since the content is unavailable at router R1, it adds the incoming interface and interest name to its pending interest table data structure and forwards the interest to the upstream router to retrieve the content, and forwards forwards the interest to the upstream router to retrieve the content. So what does it do? It adds it, and then now it is forwarding the int1 packet over here. Okay. However, before the router R1 receives a matching data packet for the corresponding interest from the upstream router, it receives another request for the same content XYZ from consumer C2. Okay, so now this is the part which you'll have to pay a little bit of attention to. So this has already reached, so this interest packet has reached XYZ. So ideally, what should happen? Ideally, the data packets should come back in this direction, correct? But it has not yet come back. Before it would come back, another interest packet called int2 has been sent, correct? By C2. Before the R1 reaches for the correspondence from the it receives another request for the same content XYZ from consumer C2. Right. So how does router R1? So basically, we don't have the corresponding XYZ MP4 in the router. So now it has been forwarded, and the pit entry has been done for the first request. How does the router R1 handle the duplicate request in its pit data structure? How does it handle it? Again, I hope the question is clear. If not, you can ask me again. So how does it right? So what does the router do? Does the router R1 add the incoming interface in its bit from which it receives the request and drops the interest? Does router R1 add the incoming interface in its bit from which it receives the request and forwards the interest to the next upstream router? Or does the router R1 immediately forward the interest packet to the upstream router without storing it in the bit? Raw router R1 neither forwards the interest packet to the upstream router nor stores its entry in its bit table. Okay, so these are the four options. Um, let's go through one by one slowly. Okay, router R1. So basically, the scenario here is interest packet has gone from R1 to the upstream location, and the point here is the interest for this particular content name, right? It has been, oh sorry, this is not int one. I'm sorry. It is for xyz.mp4. I'm sorry. Yeah. So this particular interest for this particular data or this piece of content has already been requested by whom? By C1, correct? By C1, and C1 is connected to the R1 by interface one. So only the interface is noted down. Oh God. Okay. Sorry. Right. Yeah. But before it R1 could receive this XYZ, before it would go there, another interest also came asking for the same XYZ. C2 is also asking for the same XYZ. So what happens now? Router R1 adds the incoming interface. I'm going to option one right now. Let's look at option one. Router R1 adds the incoming interface in its bit from which it receives the request and drops the interest. So what they're saying is the router adds interface 2 to it and adds xyz dot mp4, right? And what does it do? This router, they say, is going to drop interest 2. It will not forward interest to upstream. Okay, this is the first option, and this is the correct way in which NDN works. So the answer is this. Now, why does it happen this way? Why? If you know the answer, you can let me know. Otherwise, I can tell you. So why does it happen like this? Because you see, the whole point of NDN is to address content by name, of course, but it is also to save bandwidth. Now, in case if you forward this interest again, right? So this particular server, it will send two copies. So which means the whole point of being efficient is gone. Because the router knows that the same content is requested twice, it will only request the main server once for that content. And once it gets XYZ, once XYZ is present at R1, then what it will do is it will go into its bit table. These are all pending requests. Then it will send XYZ back in these directions to both interface 1 and 2. It's as simple as that, right? So this is the correct answer. And what do they say in option 2? Router R1 adds the incoming interface in its bit from which it receives the request and forwards the interest to the next upstream router. So now they're saying that it adds it and it will still forward the request to the next upstream router. That does not happen. What is the point of adding it and sending the interest again, right? That's what we discovered. So that's pretty much what we discussed right now. So there's no need to send the interest packet again, right? And router R1 immediately forwards the interest packet to the upstream router without storing it in the bit. Now, without storing it in the bit, how will the router know where to send it back to? Right. So this is wrong. You need to make an entry to show to find out where to send the piece of information that we're getting back from the main server. Right. And router R1 is neither forwards interest packet to the upstream router nor stores it. So if it doesn't do anything, if this whole entry is not even there, then C2 will not get xyz.mp4, right? So in this way, logically, you can reduce and you can figure out that the answer is A. This was a good question because it kind of like summarized how NDN works. So which of the following best describes the approach to data transmission in named data networking? Okay. Um, so data transmission is basically nothing but transferring data from one node to the other in a network, correct? So, but which of these best describes the approach in NDN? Right? Is it unicast communication between consumers and producers? So consumers are whom it's us. Producers are whom it's the servers, right? Which are kept in remote locations. Is it only unicast communication between consumers and producers? No, it's not. Right. So this is not the answer. Right. And before this, I think we can just give you the context behind this. So NDN's design enables more efficient data dissemination by simultaneously addressing multiple nodes that have expressed interest in the same content, right? So now if you look at option B, multicast delivery to nodes expressing interest in specific content. So this is correct. Why? Because in NDN, when an interest packet is forwarded, it can be aggregated along multiple paths. Correct. Because it can be aggregated, in where using the PIT in the router, which is pretty much what we saw in the previous um, question, right? Can be aggregated along multiple paths. Once the corresponding data packet is generated, it is sent back along the reverse path. Paths of all matching interest packets. This results in a form of multicast, right? In a form of multicast where multiple consumers get the data packet without redundant transmissions. Right? So option C, right? Broadcast of data packets to all nodes in the network. So see, it is not all nodes. If you're broadcasting to all, then it's redundant. It's not necessary because not everybody asks for the same content, right? So it's not the answer. And D, delivery, data packet delivery are delivered only to the nearest node among all nodes expressing interest in particular content. So it is not only limited to the nearest node, it follows all the paths that were recorded in the PIT entries, right? So this is also not. Why is this not? Because it follows all paths that were recorded in the PIT entries. Okay? So the answer is B. I'll be back in 2 minutes, all right? Right. So how does NDN handle mobility better than IP? Right. So IP is the current standard. So um, is it by using mobile IP addresses, or is it by using location-based routing, or is it by decoupling data from location, or by using a higher transmission power? So again, what is mobility, right? So we'll have to first define that. Mobility is the movement of consumers and producers. It is a challenge for traditional IP networks. Why? Because IP addresses are tied to network locations. Because one computer in a particular router will have a particular IP address, and if you move it from this house to the other house, it'll have a different IP address, right? So this is particularly a challenge in traditional IP networks. And of course, in the current world, we do handle this problem, but is there a better framework to handle it? Yes, and that's where NDN comes in. And how do they do it? They do it because it's possible because NDN decouples the content from its location. Right. So once the content is decoupled from its location, this would mean that the data is requested and retrieved based on its name rather than the producer's current network address. Okay. So what is the consequence of this? So even if the producer or the consumer moves, the retrieval of the content remains unaffected. Right? So essentially, where do we see these mobility issues? For example, you have a cell phone, right? There is this base tower. You must have read this in, I think, your wireless. If not, then just give you a small thing. So you are basically moving. You're in a car. Right? You're moving, and you're talking on your cell phone. Right? You're pretty much moving, 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 and at this point, you are connected to this network, this tower. Correct. But if you have moved to the next city, let's say, would you still be connected to this network or this network? You will switch over to this network. So your old IP address in this network your old IP address in this network. Just give me a moment. Um, just give me a moment. Yeah, sorry for that. When it comes to IP mobility issues, so we have these. Um, sorry, you move from one tower to the other, so you have to basically the towers have to understand that it's the same cell phone, the same person who's moved from a different location to a different location. So you have to transfer or be mobile with your IP address and transfer it from this place to this place. So all of these issues exist. Um, and this is one very peculiar scenario where you use it. So essentially, how does this happen? Or let's come back to answering the question, of course. So is it by using mobile IP addresses? No. Is it by using location-based routing? No, absolutely not. Is it by decoupling data from location? Yes, this is correct. And by using a higher transmission power, it doesn't even make sense, right? So the answer is C. So this is pretty much it. And the last question. Oh, oh, right. So the last question is about the content store and the router. We are saying that the router has a limited storage capacity in its content store for caching content. Of course, this is a no-brainer, right? You any device would have um, limited storage capacity, right? So what strategy does the router use to efficiently manage the limited content store space, right? Is it that the router caches the most frequently accessed content in its content store? Or is it the router caches all passing content in its content store? The router expands its memory capacity of the content store to accommodate more contents? Or is it that the router forwards all incoming data packets from the upstream router to the downstream router without storing them in the content store? Okay. So essentially, what they're asking is the router which catches, right? So we had a previous question where there was C1, C2, there was the router R1, and then there was XYZ dot MP4, right? So this XYZ dot MP4 is basically supposed to be cached, right? But so to cache anything, you need memory, right? So you run out of memory. So what strategy does the router use to efficiently manage the limited content store space is what is being right. So caching. So this is basically what is the cache mechanism being used? The question boils down to that. So caching is an important technique in NDN. Right? So caching is a very important technique. In NDN. for reducing network congestion and improving data retrieval times. However, routers have limited storage. Therefore, an efficient cache management strategy is necessary. Okay. So, what strategy does the router use? It basically just caches the most frequently accessed content in its content store. So what does that mean? If there are 10 different content, okay, let's just speak in abstract terms. There are 10 different content, and one of them, or there are 10 different contents, let's say, and some of them are more frequently accessed and some of them are less frequently accessed. So it makes sense to only capture the more frequently accessed, right? So that we can serve the requests of multiple folks, multiple consumers, right? So this is pretty much what is used. So the second option of the router caches all passing content. This is not possible, right? This is just not possible at all. It's not even physically possible. And the router expands its memory capacity of the content store to accommodate more contents. Uh, you cannot expand memory as it is because it is a hardware limitation. This is also wrong. The router forwards all incoming data packets from the upstream router to the downstream router without storing them. No, it does store it, right? That's the whole point. Not caching would pretty much forego the benefits of this in-network caching, and it will lead to more redundant traffic and increase the retrieval times. This is also not the answer. The answer is A. Right. So now that we have finished the questions for NDN, we'll just go through what was done in this whole ACN course and try to put things into perspective. And I'll just briefly speak through it because I think we've done enough work the past few weeks to understand everything. So, as it is, this course was advanced, right? Advanced computer networks, ACN. So, which means what is computer networks? Now, I'll just draw a simple diagram and then we'll put all the weeks. So, this is a simple network, right? And then you have a router, a home router, and then you have another router here, and then you have your IXP, which connects to the internet, and then you have these servers, right? These data centers. And here you have multiple nodes like this. You can go in any direction, multiple routes and multiple paths like this, and then you finally you go to the data center, right? Okay. So this is a typical, let's say, a macroscopic view of the internet, right? Now, in week one, what did we what was probably taught? Week one spoke about switching. Right? So switching, it spoke about the concepts of how these routers, right? These routers function. These routers function. What are the peculiar aspects of these routers? How much of uh, traffic they are supposed to handle, and these are all the things that which I mean, it's basically sensitize you towards the fact that these routers are not simple. They are the heroes of the internet. You cannot just like that put any uh, box there and expect it to work, right? So this was basically what was week one, right? It was about switching and routers. So week two went a little bit deeper into routers. Right? We studied about routers, but week two studied about what are all the internal data structures that are used for IP lookup, right? For IP lookup. So all the internal data structures for IP lookup, like let's say tries and different types of tries. This is what we saw in week two, right? Week three, we took a slightly more macroscopic view and we spoke about packet classification and traffic management, correct? So again, all of these are still focused on these routers or these intermediate nodes as we see. So far, we are still talking about that. And week four was also traffic management, but it also introduced you to the packet switching fabric design, right? So this is the packet switching. So so basically how these routers take a packet from this end and put it on this end. So basically the 4 weeks of the first 4 weeks talk about how packets are handled at these points. All the 4 weeks, or rather even here or even here. So all of these 4 weeks. So week five took a more magnified view. So week five introduced you to the problem of ossification, meaning how networks or internet kind of get hardened and they're not flexible for growth, right? So this is the ossification problem. And what was being done to alleviate ossification? Something called network virtualization, right? And piggybacking right on top of network virtualization, we looked at software defined networks, right? So what is the main concept in software defined networks? It is control plane and data plane, right? So we divided it into control plane and we divided it into data plane, and then we uh, abstract some functionalities here for the control plane and some functionalities for the data plane, right? So forwarding and all happens in the data plane. And under this particular paradigm of SDN, it also gave rise to something called network. This was the next week. network function virtualization. The NFV, the concept of NFV, the architecture behind it, and why NFV was needed, and so and so. Right. So this is week 7, and week 8 was programmable networks. And under this, you were also introduced to data plane programmability, data plane programming, and in that, there was also an introduction to P4, right? Originally, I thought I could explain P4 in a practical way in this particular extra class, but then I was maybe that's a bit out of scope um, with respect to the exam that you're going to get, so I deferred from that idea. So essentially, how this week we spoke about how we can talk how programmable networks are programmed, right, using a language called P4, and which part of the network is programmed. It's the data plane that is programmed, and the data plane is nothing but devices like routers, switches, and everything else. Right. This is week 8. Week 9 spoke about something called data center networking. Right. So far, week 5, week 6, week 7, week 8, right? So these 4 weeks, it was more about the overlying concept of networks itself. Nothing specific to this diagram over here, but the concept of networking itself was discussed. And I cannot put it on this diagram because it's not something that's directly on the diagram. It applies to every part of the diagram, let's say. Right? But week 9 spoke about data centers. This is the end. This is what week 9 spoke about. Data center networking. So data center networking, why is it so special? Because you have so much of data and you need to funnel this data back to the consumers, right? That's why this is important. And week 10, you were introduced to serverless computing. Right. So, and the different protocols for data centers also. So essentially, serverless computing is something that works on top of data centers. Um, it's just a different paradigm of how you use the underlying servers and how you let the consumers interact with the the resources that are provided from the data center. Right. So this was week 10, and you were also, I think, introduced to INT, right? In network telemetry and SmartNICs. Although SmartNICs are supposed to be under data plane programmability, I think it was introduced at a later point of time. Right. So week 11 introduced Quick protocol, which is nothing but a UDP based protocol, and then content distribution networks and information centric networks, ICN, right? And finally, week 12 was named data network. And this is where we stand. And this is pretty much the whole uh, course in a nutshell. So I believe the technical part of today's lecture is over. If you have any questions regarding logistics of the exams or anything, you can ask. I'll try to answer to the best of my ability. So I'll be here for another 15 minutes. If you have any questions, any of the previous classes, also you can ask me. Or if you don't have any questions, you're free to leave. Right? Okay then. Thank you. Let's first look at NFV, right? Just to briefly give you an idea of what it is and how it works, right? So that um, you can build up on top of that based on the videos that you have in this. So think of it like this: the whole of networks are can be divided or abstracted as network functions, right? So networks, if you call networks as a whole subject, you have. So what are all the components of networking? You can say routing, routing, forwarding, filtering, packet filtering, right? Firewalls. So these are all different types of network functions. So the previous paradigm, what it used to do is you used to have specific hardware to run each of this. You used to have specific hardware. Um, so when you have this specific hardware, again, Jeev, when I'm explaining, if you have any questions, you can interrupt me then and there. All right, so that's fine. You don't have to just chat. So we have specific hardware that kind of caters to all of this. So there was a strong coupling between network functions and hardware, right? So one kind of hardware could only do forwarding. One kind of hardware can only do packet filtering. One kind of hardware can only do routing the best. Something like this, not exactly like this, but I'm just abstracting the whole thing and giving it to you in a digestible format, right? Okay, so this was the paradigm. But what NFV did is NFV, it considered all the network hardware as same. We call this network hardware, right? But on top of this, I will be running routing, forwarding, firewalls, etc. So essentially, you see the difference here. The difference is NFV, it transforms traditional network hardware functions into software-based solutions. Correct? Very similar to our, let's say, current paradigm of cloud computing. So this allows network operators to run their network services on commodity hardware and standard servers instead of specialized and dedicated hardware appliances. So this NFV, it is used in conjunction with SDN also. Right, so essentially, this is what NFV is. You abstract network into different functions, but you can kind of like spawn these functions on, let's say, CPU hardware also, or some specialized network hardware. So you have multiple ways of doing this, but this is the fundamental concept of NFV itself, right? So this is it, and I think this is enough. Or do you want some more details on this? Let me know, right? But when it comes to DC networks, spine or leaf, right? So if you look at I mean, I think instead of drawing, I think I should copy and paste it, or I don't know how. Okay, fine. So data center networks, right? Now, I think you know why data center networks are very niche. They handle a lot of traffic, and you need to throttle traffic out as fast as possible, right? Data center networks. Yes, leaf spine. Right? So the it looks like this. So there are some spine switches in the organization, right? Spine, spine, and then you have some leaf switches. and then we have some leaf switches. Right, so it's just a way of organizing these switches in the data center. That's all. So you can connect all of these switches directly also. You can do all of this directly also. Right? Or you can organize it in a leaf spine way. Now, why is it being organized in a leaf spine way? Because it makes it more efficient to transfer data, or it increases the bisection bandwidth. There are all of these um, specific terms, which I think you can go through the videos again and understand this. So essentially, yeah, and redundancy as well, right? So it increases redundancy as well. Perfectly said, yes. So essentially, this is pretty much what it is about. What is there to talk about leaf spine architecture? So if in more specific terms, I'll just write it down. So spine switches, they form the core layer. So these are high throughput, non-blocking switches. Right. Next is leaf switches. They connect directly to servers and act as the access layer. Right. So again, leaf switches are connected to servers here. Sorry. Access layer. So also every leaf switch connects to every spine switch. Right. So this leaf switch is like this. This is connected to this, and this is connected to this, and this right here. Spine switch. So what this does, this ensures equal latency and bandwidth between any two leaf switches. Right. So this is pretty much the summary of um, what it is, what this is, and of course, what are the advantages? East-west traffic optimization, scalability, and ECMP, equal cost multipath, meaning there is multiple paths between any two endpoints. So these are all the advantages. Again, it's just a summary of it, and yeah, let me know if it's over, or I mean, if you have any more questions. All right. So if there's nothing more, then we can end the session. And yep, all the best for your exams, if at all you're taking it. All right. Okay, then bye bye. Likewise, guys. Thank you for attending. I know 2 hour classes are very tough, which is why in the middle I made it into 1 hour classes almost. I tried to compress it into 1 hour, 1:15, because I think it's difficult to still put it for 2 hours, both for you and me. But yeah, thanks for attending, and I think I'll end the session now. All the best, guys. Bye bye. See ya.